Hello and welcome to this video. In this video we're going to be looking at the topic of uncertainty. So we've previously looked at errors and how the errors are formed, and now we're going to look at uncertainties and how we would do calculations with these uncertainties so that we can find out what range our actual value can lie in. Okay, so the first thing we need to do with these uncertainties is to define a few words. So whenever we make a measurement, we need these measurements to be as accurate and as precise as possible. But there's a difference between accuracy and precision. Okay, so accuracy means that the value obtained by this experiment, so in the previous video I used the example that G needs to be 9.81 meters per second squared, or newtons per kilogram. The value obtained by the experiment is near to or exactly the expected value. Okay, this is what we get for having an accurate value. Okay, so an accurate value means that that number needs to be close to what we expect it to actually be. A precise value doesn't have to be accurate. Okay, if I wanted a very precise measurement, I could measure that G is 246.39472615434 meters per second squared, which is a very precise measurement because I get it right down to the 0.0000000000004, but it's not accurate at all because this is 246. We're miles away from what our expected value is, and so although we have a very precise measurement, we don't have a very accurate measurement. So the precision is a measure of the degree of accuracy that you have. Okay, so the precision is dependent on how many significant figures you are rounding to obtained in the value. Okay, so in order for a measurement to be a good measurement, it needs to be both accurate, so close to the expected value, and precise, meaning we want a large number of significant figures. If we have a really precise value but not a very accurate value, we can disregard it. If we have an accurate value but not a very precise value, then it's going to be, so if we get a value that's maybe 10, okay, but it's not very precise, then we'll have larger uncertainties on it. And if we have larger uncertainties, we have more opportunity that it's going to lie between what we expect it to be. Now, these are the general two that they will ask you to compare the difference between, but we will also have to know what is the meaning of the word resolution. Okay, so we need to have accurate and precise values that we measure, but that in order to do that, the resolution of the instrument that we're using has to be quite high. So the resolution is just the smallest change that we can measure, smallest change measurable by that instrument. So if we have, for example, a ruler, let's say it's a meter long ruler, we know meter rulers we can measure to the nearest millimeter, and so our resolution is to the nearest millimeter. Okay, although what we would say is that our uncertainty on that then is going to be half of the smallest division. So this is called absolute uncertainty. Okay, this is now going into what are the different types of uncertainty that we can have, and the first is absolute uncertainty. If we can only measure something to the nearest 1 millimeter, okay, so let's assume this length that we're measuring, we can only measure to the nearest 1 millimeter, it means that we have an uncertainty that if we're approximating it to be to the nearest millimeter, we could actually say that it's half either way, half a millimeter, because if we were to zoom in on this image and look at just this section, so let's say this is all of the millimeter gradings. Okay, if we were to see that the rope ends up here, we would have to round this to here. And which one could it be? We'd have to just decide one or the other. We couldn't probably decide in between the two, because we'd still have some sort of uncertainty on that measurement. And that uncertainty is going to be half of the resolution. So half of the smallest degree of accuracy that we can make with this instrument. Now sometimes we'll have to account for this absolute uncertainty twice. So, and again, in the example of lengths of something like a ruler, if I was to measure, if I was to get a ruler like this, and I was to measure the length of something, and I put it dead in the middle, not only do I have an uncertainty on this side to see where its 0 is, but I also have an uncertainty on this side. Now, if we've just said that the absolute uncertainty on a ruler is half a millimeter, that means that I've got half a millimeter uncertainty on both of these measurements. So in total, I have 1 millimeter uncertainty. Okay, and this is what I mean by absolute uncertainty. It's always going to be half of the resolution of that device. But we can also have a measurement called the percentage uncertainty. Now the percentage uncertainty, and sometimes you can also get just the fractional uncertainty, but we tend to work more with percentage uncertainty. I'm going to write it as PU. The percentage uncertainty is just the absolute uncertainty. Absolute uncertainty divided by the measurement that we've actually made. Okay, so it's saying out of what we've actually measured, how much of this could technically be wrong. Okay, and so if our absolute uncertainty on the length of this is 1 millimeter, let's say this is 1 times 10 to the minus 3, because I want to have this in meters, and we find that the measurement of this is 60 centimeters, so its measurement is 0.6, then we could do this and then times it by 100 to get what the percentage uncertainty of this measurement is. Now what this means is the larger our measurement, even though the absolute uncertainty can't change, the larger measurement we have, the smaller our percentage uncertainty becomes. So this is going to be why most of the time when we take measurements, we're going to measure over much larger variations or much larger gaps in between two things we're trying to read, because if we increase the measurement that we're making, we're decreasing our percentage uncertainty. Now this percentage uncertainty will be equal to 0.167. Now this is rounded to 3 significant figures. What you'll find when you're writing out these values for uncertainty is you want to make the significant figures that your value is, your measurement, equal to the same amount of significant figures that your uncertainty is. So in this case, our measurement was 0.6, so we want our uncertainty to be to 2 significant figures, or sorry, 1 significant figure here. So our first significant figure is 1, so we need to round that up. So our measurement becomes 0.6 plus or minus 0.2%. Okay, and on here we'd have to make sure that we're actually putting in that this is meters. Okay, and then we take 0.2% of this either side of that, and that's our percentage uncertainty. Okay, now this is how we get those individual uncertainties, but when we're actually going to form a calculation for something, we can only measure. So let's take an example of resistivity. We can only measure certain things in this formula. So in order to work out what the resistivity of something is, we know the resistivity is the resistance times the area divided by the length. We can measure the area, we can measure the length, and we can measure the resistance, but we need to calculate using this equation what the resistivity is. So how would we actually combine things if they're in a formula? Well, we have general rules for those things. So our general rules for combining uncertainties is that if we have an equation where we are adding two things or minusing two things, so when we add or minus, then what we do is add or minus the absolute uncertainties together. Okay, so this is exactly what we did when we were looking at the ruler, for example. So we were saying that the total length of the ruler, of the string that we were measuring, was actually this measurement minus this measurement. And so because we were minusing them, their uncertainties actually just sum together. Okay, so we can't minus uncertainties, we can only add them together. So if we're going to take two measurements and we add the measurements together, their total absolute uncertainties are going to sum together to make more uncertainty. Okay, if we want to, so when we multiply or divide two things, like in the case of resistivity, we add together all of the percentage uncertainties. Okay, so we would have to work out the percentage uncertainties for each of these things: percentage uncertainty for the resistance, then the area, then the length, and then we just add those three percentage uncertainties together, and that would give you the total uncertainty on that resistivity. And our final thing here is what happens when we have powers. So if I put something to the nth power, what do I do with that? And all I'm going to do is multiply the percentage uncertainty by whatever the power is. Okay, so if I raise something like to the power of 3, then my percentage uncertainty is now triple what it originally was by the power. Okay, so if I square something, my percentage uncertainty doubles. If I cube something, it triples, so on. Okay, and these are our general rules for how we're going to combine uncertainties. Now, what I've explained in most of the videos is that if you're going to make a measurement in a practical, we're usually going to use graphs, because graphs allow us to have much less uncertainty on measurements, because we can put loads more information all in the same thing. It's easier to rule out what anomalies we have, and then we'll get more accurate results. So let's look at how we would make a graphical analysis of uncertainties. So graphical uncertainties. Okay, so when we make graphs, we usually have things trying to be linear. So we will choose two axes such that the graph that we make is usually a linear one. Okay, this tends to be quite straightforward. We obviously are not going to get a line. Our data will probably look something more like this, and we'll be asked to draw a line of best fit. Okay, now that line of best fit is kind of open to interpretation. We can have one very good line of best fit, then one very bad line of best fit, and then we could see how those lines of best fit are going to affect what the value would be, and therefore we can calculate uncertainty just from these graphs. But how we're going to do that is, in order to work out what the worst line of best fit is and the best line of best fit, is to say we need to have some errors on each of these measurements, which we will have because we have some absolute uncertainty. Now, what we're going to do to show that we have errors on these measurements is use something called error bars. So error bars indicate that there is some error on this measurement, saying that at this, let's make this, I don't know, a distance time graph, that at this exact time, we're not quite sure what the exact distance is, but we know it's in this range between these two values that we would read. So each of these data points here, we can add error bars onto. Now, error bars don't always have to be vertical. We could say we're also not sure how long it was there for, so we have some error on the time, but we're just going to work with the vertical ones for now, but just know they should be horizontal. They could be horizontal as well. And so what we would do in order to get our worst line of best fit, we want to go as low as possible, but making sure we're getting through as many as possible. So I would say that this data point and this data point are probably going to be looking like anomalies in this case, okay? Purely because they're not really in line with these 4 data points. So my line of worst fit, I'm going to put in red. So my line of worst fit is going to go through the bottoms of all of these uncertainty bars, and then my line of best fit is going to go through the very top of them all. Okay, or my shouldn't really call it a line of best fit. My other worst line of best fit is going to go up like this. Okay, and so hopefully we should find that these are going to get 2 different gradients. So actually it would be more like this second one, because it's going to have a slightly different gradient here. And then what we would do is we would work out the gradient of the blue one, then the gradient of the red one. We would draw an actual line of best fit, which should be directly in between the 2 of them and passing through as many points as possible. We then want to find out what's the difference between the best and worst gradient. So we'd probably have the highest gradient versus the lowest gradient would be probably a better way of saying it. So the highest, I'm going to call gradient M, minus the lowest M divided by the best M is equal to the uncertainty in that gradient. That gradient is usually going to be the measurement that we're trying to make from this practical. And so this means we take a really high gradient and we take a really low gradient, but are still acceptable because they fit within these error bars. We take the difference between them, divide them by the best gradient that we have, and that will give you your uncertainty on this gradient. So this is everything you need to know about uncertainties. Hopefully this is making you hate uncertainties a little bit less, because they are very useful, and you'll find that if any of you are going on to further education in physics or engineering or anything where you'll have to do lab work, uncertainties are going to quickly become your best friend, because they'll allow you to, even if your value is completely wrong, as long as it fits within your uncertainties, you can say it's an acceptable value. So this is uncertainties. Thank you for watching.